In this video we're going to see how to use calculus to find the volume of a solid of revolution. What do we mean by a solid of revolution? Well, as you can see on the screen, if we take a function y equals f of x, that's the line along the top there, and we then revolve it, send it sort of spinning around if you like, the x-axis in this case, then we get a nice symmetrical solid generated by that movement. So up until now with calculus and in most of our function work we've just had a y equals fx. It's just stationary still. But here we do something quite different. We get the function and then spin it right around at one of the axes, and that makes a solid. And that solid we can find the volume of using calculus. Let's have a look at that in some more detail now. Let's start then by looking at the volume that's created if we revolve a function about the x-axis first of all, and then we'll look at doing the same thing around the y-axis. But here's our function, that little red line, some linear function, y equals 2x, or goodness knows what, y equals some linear function of x, and we're going to revolve that around the x-axis as the arrow shows, and you can probably tell fairly quickly what sort of a shape that will make. We'll get a nice cone, and the cone at its base will have a radius of y. And the interesting thing, and this is where calculus comes in, that cone can be thought of as made up as a whole series of very thin disks. So here it's like looking at the base disk, and then there'll be a lot of smaller and smaller disks lying on beside that, going to the left, to make up the whole cone. So the radius of this base disk is y, this y here, and its thickness, the thickness of this disk, we're going to call dx. And this disk can of course be any of the disks along here. Y is going to vary depending on where we are along the axis. So what's the volume of this small disk going to be? Well, we know the volume of a three-dimensional object is the area of the cross-section times its thickness. So in this case, what's the radius? This is a circle, of course. We have a disk here. Cross-sectional area is a circle. Area of a circle is pi r squared, so in this case it's pi y squared. And then we multiply by this thickness dx, this very small thickness you're getting used to in calculus. Strictly we should call it delta x and then take limits, but I'm sort of shortcutting that a little bit for you here. So the volume of this small, the very thin disk we can call dv, strictly delta v, but we'll just call it dv, and that's going to be pi y squared, the area of the cross section, times dx, the thickness of the disk. And we can calculate the areas of all of the many very thin disks right up to the tip of the cone here. And then how do we find the total volume? Of course, we just add them all up. We find the sum. And in this particular case that I'm showing you, we're going to be integrating from x equals 0, adding up from x equals 0, and all the disks right up to x equals x naught, our stopping point. So that's what we're saying here. Add them all up from 0 to x naught, the volume of these small thin disks. And that gives us the total volume of this cone. And that's as simple as that. Just to make sure you understand it, we'll repeat the process, but this time revolving around the y-axis. Let's have a look. Here's our function again in red, this time going around the y-axis. So again we get a cone, this time it's standing up, and this time its radius is x. So the radius there, the radius out here is x, and whatever the value of x is at the particular disk we're looking at. Okay, so similar process as before. The radius this time is x, and of course the thickness now is a small tiny bit along the y-axis instead of before it was a small tiny thickness along the x-axis. That was dx. Now, because it's a small thickness along the y-axis, we of course call it dy. And so this time the area of this thin disk will be pi x squared and the volume multiplied by dy. So the dv, the volume of the disk, is pi x squared dy. Volume of the whole cone, integrate from 0 up to our stopping point y0, pi of x squared dy. All these little disks right up to the stopping point y0. Now, we're going to go to this GeoGebra lesson, GeoGebra demonstration, and see what we can do with much more complicated functions than just these linear ones I've shown you. This was useful just to get the principle, but that applies to really quite complicated functions which give far more interesting shapes than just a cone. So let's have a look. Here we go. Here's a particular function, x to the fourth, blah, 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 quite a complicated one. And how would you do that? Well, pi y squared dx, the integral of, and so you would have to square this. This is your y. You could square that. I mean, it would take you a while, but you could do it. And then you take the integral, you evaluate it between x1 and x2, and you should get that number there. Let's have a look at how this thing works, the wonderful shape it generates. So that was our base function, and we can vary the limits, x1 and the x2, and get all sorts of different shapes. So there's the solid being generated for you. And then by using calculus, you could quickly find, well, I don't know about quickly, but you could find the volume and compare it with that. Well, I suggest you do actually do this. One, for just getting wonderful shapes, but for testing your calculus, put a simple function up here that you then have to square. So pi y squared dx, integrate that, and see if you do get the value that they give you there. You see, if I stop that, I can change these limits here, just dragging that along. It gives me the new volume of revolution. So this is quite a powerful and very useful tool. It gives you immediate feedback on your algebra, first of all, if you squared it properly, and then your calculus doing the anti-differentiation properly.